Hey, good morning, everyone. My name is Abdul, and I'm a systems engineer at Facebook's data platform, working on Spark as a service. We develop and provide Spark as a service for the greater Facebook community and different teams. Today, we'll be talking about powering custom apps at Facebook using Spark script transformation. As part of this talk, first I will explain what script transforms are. Then we'll look at some few use cases for script transformation at Facebook. Then we're going to discuss the developments that we made to make this work. And also we're going to look at some efficiency analysis and results, as well as explain the transform execution model. Well, before talking about script transforms, briefly I want to talk or highlight Spark's journey at Facebook. Spark started as an experiment in 2015, and over the years has evolved and became the largest engine at Facebook by CPU. And script transforms make up a considerable percentage of Spark's workload. Therefore, reliability and efficiency are our top priority. All right. Well, first let's explain what script transforms are. I'm sure this topic might be new to you, but I will make sure to cover in detail. Well, script transforms is an operator that allows users to run custom code to process data externally, while relying on Spark for ETL and data processing. The SQL syntax shown here shows the components of a script transform query. In particular, there are three components: inputs, and the transformation binary or the application, and also the outputs. So this is the simplest query for transforms, in which we have inputs highlighted, and also the script as well as the outputs. Now, looking at the execution plan, it also looks similar. There is a script operator, or there is an operator called script transformation, which captures the information about the transform, in particular input, output, and also the binary to execute. And in this case, our transform reads from a source table, writes the information to an external process, and reads back. So the execution is visualized here. As you can tell, Spark is in charge of the data access and ETL, in particular reading and writing data from the output and input tables. But at the same time, Spark also streams data into the external process that the user provides, and also reads back the results, and then applies further ETL if there is, and saves the results back to the output table. Well, now that we understand what script transforms are, maybe let's talk about the motivation behind them, or why do people use them, at least in Facebook. So the first thing I was going to mention, maybe unlike UDFs or user-defined functions, which, as we know, have to be written in Java or Scala and need to be run inside the JVM. Transform code runs in an external process separately, which gives the ultimate flexibility for the user to do whatever they want. You're not limited by a JVM language or limited by the Spark's environment or Spark's API. You can do anything. And we're going to look at some few examples. So the flexibility is one of the main reasons why people use, or why engineers use transforms at Facebook. Another important point is efficiency. As you know, even though you can implement some logic in UDF, sometimes that logic can be implemented more efficiently in C++, especially when the binary is compiled with optimizations. That often leads for reduction in CPU and for reduction in latency. Also, I want to highlight maybe there is also another venue for writing custom code, which is PySpark or Pandas UDF, but that's also limited to Python. Most of transform workload we're going to be discussing is mostly written in C++ for efficiency and flexibility reasons. Now, there is a contract or kind of cooperation expectation between Spark and the process and the transform process. The transform process provides the custom data processing logic, while still relying on Spark for what Spark is good at, which is the ETL, data processing, distributed execution, as well as fault tolerance. Spark already is good at these components, so why not take advantage of them, and at the same time offload the custom processing somewhere else. For example, Spark is optimized for ETL, reading, partitioning data, applying filters and whatnot, but PyTorch is optimized for model serving, for machine learning workload. So we're gonna go over a few examples of how these two components that seem to be separate actually work very well together. All right, second, now that we explained what transforms are and why they're used, we're gonna look at some few use cases for script transforms at Facebook. Since the development, or since Spark Transform support is added more than a year and a half ago, it has been growing, and adoption rate has been increasing since then, up to the point where 15% of Spark CPU at Facebook is allocated for script transform workload. And I would think the main reason behind it is mostly flexibility and efficiency that the transform operation or operator provides. And today, maybe custom user code, which is transforms in UDF, make about 45% of query count at Facebook. And in CPU, about 20% of CPU allocated goes to custom or user code, which includes mostly transforms and some UDFs. So it's a very significant, considerable percentage of Spark resources that go to run this one operator. And the primary use case actually at Facebook mostly goes to enabling custom machine learning workload, such as batch inference, feature extraction, indexing, and further. We're going to look at two examples in detail on how transforms are used in practice at Facebook. So first use case. This might be a bit overwhelming, but we'll go over it and explain what this query is about. So this is a Spark SQL query for a transform job. So the first line includes that file, which includes the transform resources. As you explained earlier, transform jobs rely on the user's code. So the user has to provide a binary that provides a custom logic. In this case, there's inference engine and also a model file. This is an image classifier batch inference use case, in which we have a PyTorch model takes in images and as an input, and as an output, it gives back the categories or labels what these images are meant to be. So this input includes, as you can see, the second line, transform ID. There's ID, metadata, and image. And those are serialized in JSON format to the transform process. And the output is a map, which includes information about the categories and their confidence. So label confidence, what is a typical image classifier output. And the same thing also, the input and output formats are JSON, something we all understand. Now, this is part one. Part two of this transform is the user code itself. As you mentioned, transforms are two parts. There's the user code, there's a Spark SQL query. Now, the SQL query is simple, or the user code's part is simple. Mostly, we have an iterator over, so every time Spark writes a row, the transform receives it. In this case, we have an image data, so we apply the prediction, which is a custom user logic. We're not showing it here, but their processing logic can be anything. In this case, applying the prediction function to find out the categories that apply to this image, and then write back the information to Spark. So putting these, now let's put these all together. At a higher level, this shows the systems level of script transforms. Now, on the left side, you have the Spark executor, Spark GVM, where the RDD is stored. So Spark has iterates over the input, which is the rows of images, and serializes the internal row, which is Spark's internal data structure, to JSON, and passes that over the standard input to the process. Now, also to know that this process, the external process, is also invoked by Spark. So Spark is a parent for the transform process. Now, I'm sending the information by over the send input to the process. Now, the process is opposite. It deserializes the JSON object to C++ objects, and then applies the processing logic, which is in this case is a prediction, and then serializes the output back to JSON and sends it over send output to Spark. So you can see two serialization. Serialize Spark, serializes internal row to JSON, then at the transform process the opposite, and then to JSON again, and then at Spark we do also the last deserialization back to internal row. And you can tell the biggest difference, something to highlight is the input and output. So you can tell the input is images, could be in binary format, could be anything, but the output is the JSON object contains the labels and the confidence. That's where transformation happens. Now let's look at another example. which is also another popular use case that shows the cooperation between Spark and script transforms. So batch indexing usually means is a transform process that allows users to build indices for fast online access later. So using Spark to read large portions of data and then build an index that can be used for some access for real-time access in different services. But one thing to highlight here from the query can tell there is the transform input. So there are two fields, the shard ID and the data, that are serialized using row format delimited, a very popular and flexible serializer. But there is no output. So this transform only consumes data from Spark but does not write back anything. And also something to look at, to note also, there is the last line, cluster by. This transform expects the data to be sorted and partitions by ID. So look at the execution part. So unlike the first case, the mapper transform, this is a reducer transform. The first stage is a pure Spark SQL stage. We do the Spark would read the data, will write the IDs to shuffle, or write the shuffle data to temporary storage based on ID. And then the second stage, or the due stage, is where the transform happens. So the second stage tasks will read the shard IDs. And since each task has one ID, each task streams the data to the transform, which builds its index, and then saves it to some offline storage. So this shows the cooperation, the coexistence or cooperation between Spark and the transform process. Spark is in charge of the partitioning and sorting, while the process is in charge of the custom processing, which is the index building here. Now that we look at some examples and some use cases in detail, let's take a deep dive on the development work that we did to make this all work efficiently. Well, the multiple parts for development. The first one, or the first set of changes that we made were involved improving the operator logic. Currently in open source Spark, transform operator exists, but it's very limited and primitive. Some of the summary of the changes we made to the operator itself, which is first, includes process invocation, which means Spark becomes a parent of the transform process, which means Spark is, when Spark finishes, the transform process are automatically cleaned up. As well, we introduced a new class, IO schema, to handle the serializer, deserializer config and schema, as well as adding a monitor and error handling logic. As you can realize, the external process can have its own failures, and which might make it hard to debug for an external process. All these failures will be happening inside the external process, which Spark has no knowledge of. So we introduced another class to monitor the errors and to surface them back to the user. Now, another important part of transforms is the serialized, deserialized logic. Maybe as of most of you know, most of the overhead will happen between conversion of Spark data types to C++ or the transform data type. So we're going to go in detail on the options we have and how we made this efficient. The first serializer, or the first communication format that is available and used, is JSON. So we implemented the first interface using which is called delimited JSON serializer or deserializer, to allow users to use JSON, which is a flexible format to transfer data from Spark rows to C++ using JSON. So a lot of JSON parsing and decoding is involved. Another serializer protocol we also included, which is the flexible or row format delimited. Very popular and flexible. Existed since Hive introduced it early on, and also still in use. This serializer is more flexible. Unlike JSON, here you can control what some parameters about what the characters use to split fields and split columns, like array lists or maps and whatnot. So it's a bit more flexible, but very much similar to the JSON serializer format. Now, looking at these two serializers, they're mostly we refer to them as text-based SERDs, which using text to serialize data. This is good for development, but has a big downside, which is the overhead involved in converting data types from Spark to JSON and JSON to C++ and vice versa. So this was not satisfactory to be used in production given the overhead. So as far as development is concerned, using them is sufficient. But for production, we had to find something else. Both of these two SERDES also exist in Apache Hive. So they are now, they did implementing them at Facebook allowed migration from Hive to Spark to continue. But for efficiency purposes, we had to find some newer format. Now, for production serializer, well, first we knew we had to find something new, find a newer format. First, text-based SERDES have the downside of overhead. So first, using a binary SERDE was one of the first requirements. Finding a binary SERDE to convert data types of Spark to some binary format. Now, binary format means there is no longer text-based encoding overhead, and also it's more compact. Now, another criteria that matters that we put also as in terms of design requirements is zero copy. So what does zero copy mean? Well, as you recall, in the case of JSON, when JSON writes data over certain input to the user or the transform process, the transform process then has to parse the JSON back to C++. That means copying the data somewhere else, creating new objects and new instances, which could be which could include a lot of overhead. Zero copy here means the ability of the transform process to read the data directly without parsing or unpacking, pretty much with zero overhead. We were inspired by another use case that the Facebook Android team worked on, which is the flat buffers. Flat buffers, also another zero copy serializer that did help improve Facebook's Android performance. The very last requirement we had for binary SERDE, which is the word aligned data. Word aligned data means having data stored at a word or a 64-bit offset. What does it mean? Well, it means, or it allows for SIMD optimizations. If data is aligned at 64-bit offsets, then you can apply vectorized operations at the CPU level. So taking all these three requirements, we looked into options, we looked into open source and available serializers, deserializers that are used in applications today. So the first one, which is the lazy binary SERDE used in Hive, it satisfies some of the requirements. It's a binary SERDE, but it doesn't allow for zero copy or word aligned. There's protocol buffers or proto buffers, also thrift. Both are similar. They do not contain zero copy features. Also, they're mostly suited for remote procedure call, not localhost. As you recall, in transform cases, we have the Spark JVM and the transform process. Both are running on the same host, not remotely. There's flat buffers and Cabin Proto and other zero copy serializers or codecs. They both satisfy most of the requirements, but they lack the convergers between Spark, Spark internal rows and their respective formats. Apache Arrow is another good option for the future. There is still some development that's being done for complex types that is not there yet, but in the future that could be the solution. But these are the kind of the solutions we were considering at the beginning of binary SERDE. Now, well, we found our solution, but it was not one of the lists we found above. We found it actually in Spark itself. So Spark has a data representation format called unsafe row, which satisfies all the requirements we looked into and also is already part of Spark core since 1.6 and has available converters from internal row, which is what the RDDs provide, and to unsafe. So unsafe row internal row conversion is already available at Spark. Hence, that was one of the reasons we ended up picking or choosing unsafe row. Now, to explain, well, first you might ask, what is unsafe row SERDE? Well, unsafe row is a row memory backend format for Spark rows. It uses the JVM's unsafe API, which is a very fast API to access and copy data in this representation. This is already part of the open source case since 1.6. It's not new. And the format is categorized as variable length. So you can pretty much, it can encode any data type that a Spark row contains. So any Spark row can be converted to an unsafe row and vice versa very efficiently. Further, Spark row introduced, unsafe row Jira introduced, the one we just saw above introduced all the conversion types or conversion functions for all primitive types plus structs, but not maps or arrays. Another PR that was added later added support for map types and array types. So in similar case, unsafe map and unsafe array data types both provide the same row memory backend for rows and maps respectively. Now this is the Spark. Now we just looked at the Spark side. Now maybe recalling back for JSON, row format delimited or JSON both both already have C++ deserialized or parsers that exist today. Anyone can parse JSON in C++ already with a lot of options that are available. But in our case, since we're using unsafe row format, we had to provide or create our own C++ serializer or deserializer for unsafe row and for our clients. So what that means, we had, for primitive types, the conversion is simple. Integers has a mapping to int32 and booleans and floats and whatnot. Now strings, arrays, and maps, we had to create our own data types in C++, which correspond to the unsafe row list and string and map. Now let's see how all this works together, how this works together. So let's take this example. Now on the left side, you see this is on the left side we have a simple transform query. We're writing an integer using the unsafe row format, which we are specifying the query, and reading back the value. Now we also provide the users, as part of this development, we also provided the unsafe row SIRD library in C++ that allows users to interface with Spark's unsafe row data types. So in this case, it's simply as iterating over the rows and then simply calling input get ID will give you the unsafe data ID in C++ type instantly. And also the other way, when writing back data from C++, we also provide the converters. Now these converters are very efficient. As I mentioned, this is a zero copy format, which means in C++ we can actually access the content of the array or the object or the map or any primitive type without copying or deserializing. So pretty much it's very efficient and removes the overhead that JSON adds. We will look at the overhead benchmark in a bit. And also as part of the library, we also provide getters and setters functions to allow users to focus on their custom processing logic and not have to worry about data parsing and data management. All right, back. So this is to summarize the core development we did. So text-based SIRDs, we have the JSON and row format delimited, which are both were carried over from Apache Hive. That was the first iteration of development. Secondly, we described how we had the addition of the binary serializer, which is the unsafe row SIRD. First, we read the requirements, and also we explained how we chose unsafe row as opposed to other options. So now having all these three options, we can look at how all these things interact, or how the benchmark in terms of CPU compares for all of them. Before we do that, we're going to look at one last thing. So one of the last development additions we added, which is the aggregation and projection support. So the current Spark open source does not support aggregation and transforms. Like in the case of you want to transform ID, but also you want to apply a function before you apply it or transfer it to the transform. So that was the last case of these are categorized as transform aggregators, which is instead of using UDF, you're using the transform itself to apply the aggregation function. So that's one of the last milestones of core development that we added. All right. Well, now looking at now we describing the development effort. We can look into the benchmarks and how the serializers perform in production. Well, as you recall, Spark is already efficient on its own. When it comes to ETL, Spark already performs very efficiently using the Catalyst and Tungsten backends. So when it comes to ETL logic, there is no overhead. It's already efficient. And by the same token, the transform process is also efficient on its own. Well, most certain C++ and compiled with optimizations, both the GVM and the transform process are running as efficient as they can. Now, the overhead is introduced in the communication protocol. The only place where the overhead can happen or can be introduced is when data is exchanged from the GVM to the process and vice versa. So we're going to look at this and look at this in detail again. So first we're going to look at one of the queries. We're going to look at one query where we're using JSON to serialize data back and forth to the transform process. So this is stack trace for one test job. The highlighted stack traces represent the CPU time spent on serializing and deserializing. So 30% of Spark CPU allocation was used just to serialize and deserialize data, which is relatively expensive. Ideally, you would only want to spend your CPU time on performing a processing logic, not on data exchange and movement. Now let's look at this is looking at the transform process on the other side. So we look at the Spark's overhead. 30% of the time, or CPU roughly, was spent on SERDI logic. Now in the transform process, maybe it's even worse. About 50% of the CPU time at the transform logic in C++ was spent on JSON deserialized parsing. As you recall, there are two SERDI round trips. The Spark will do serialize and deserialize. Also the same, if you mirror that, the transform process is the same thing. So the transform process deserializes or parses JSON and then encodes it back again as a result. So half the time in this transform process is spent on JSON SERDI, which is very expensive. Now, the conclusion from these cases that we noticed is in text-based serializers, the overhead is non-negligible. And that even becomes worse for complex types. Serializing a map, an array in JSON is very expensive, and also parsing it. And in observation, this could be 50 or even 70% of the CPU time of the pipeline. So 70% is spent not doing the logic you wanted the pipeline to do. So what is the solution for this? Well, using an efficient serializer. So as you recall, in our core development, we introduced unsafe row SERDI. Now let's see how that does in benchmarking. Now, before we look at the benchmarks, we're just going to highlight the interaction of unsafe row SERDI and the transform process. So we have looked at a similar case, but for JSON. Now, in the case of unsafe row, on the Spark side on the left, we can see the internal rows that are serialized to unsafe row very efficiently using the JVM's unsafe API. That's already done in open source currently. Now, the same data, the unsafe row bytes are sent over the wire, over send input to the transform process. Now, since you mentioned earlier, unsafe row is a zero copy SERDI. That means we can access the data types and the content without parsing them. So hence we only do mapping. We map the unsafe row bytes to a C++ object. There's no copying, no new objects, nothing. So it's very instantaneous. The same thing, also by the same token the other way, when we're mapping C++ objects to unsafe row. We provide unsafe map and array and all these types. So as long as our users use the unsafe maps or the lists that we provide, the conversion is done with zero cost or overhead. Now, the same case, when the transform writes back the output, uses the standard output and also unsafe row. In Spark, we take the unsafe row result and map it to internal row and iterate over that until the last row is sent. So now let's look at the benchmark results. So the way this works in terms of the transform process in Spark, this is the same as JSON. The only change here is the communication, is the protocol or the codec format. Now, if you recall that in the earlier example, in our case with the the SERDI overhead for JSON was 30% for Spark. Now it's merely 1%, like about 30% or 30x, actually 30x reduction in overhead. And look, similarly, at the transform process, the overhead dropped from maybe 50% to about 10%. So 5x reduction in CPU overhead when using unsafe row SERDI. So it's a win-win for everyone, for the transform process and for Spark and for the resource allocation. Now, we made also synthetic benchmark to compare the unsafe row or the binary SERDI efficiency. So in this chart, we're looking at about 6 different data types, primitive data types, and also we have 3 complex data types, arrays and maps and integers, which are becoming more extensively used at Facebook. So binary format pretty much always performs better. Now, but in particular, it's worth to know that for complex types, maps and lists, binary format performs much better. We're talking like 8x or 10x times better. Because as you recall, JSON is not optimized to serialize complex objects. It will incur a very expensive CPU overhead as a result. So the observation is when using binary SERDI, we observe about 4x reduction in end-to-end CPU usage by transform pipelines, which is very significant. Taking into account transforms make up 15% of Spark's overall CPU usage. So this is a huge efficiency when for our core engine. Now, finally, the last thing, we look at the transform execution model. So now we have looked in detail about how the communication protocol is done, and we looked at the JSON versus unsafe row SERDI, and we made the case for the efficiency. We looked at the benchmark and why binary format is always more superior. We can look at the higher level execution view. So for Spark transforms, as you recall, transforms require additional resources since they are running externally in a separate process. In this case, we have the Spark containers. They have the yellow boxes containing the transform processes. Therefore, we need to ensure in our resource requests we account for the memory usage. So unlike in Spark SQL, in this case, our container sizes are are increased to account or to give room for the transform processes. Now, when it comes to resource control, which used to be a very painful point of operation, as you recall in GVM, there exists memory limits that controls how much the on-heap or off-heap objects can grow. So there is XMX, SMS, and other limits that controls how much the Spark SQL or a Spark job would use. And that only applies for pure Spark SQL jobs. As you recall in transforms, we have an external process, which means the limits that we set for the GVM no longer apply, or actually no longer relevant for the external process. Well, the solution, very simple, using C group V2 containers. So we partnered with the kernel team at Facebook, who is in charge of kernel development, to make use of C group controllers. In this case, we made use of 3 controllers for the memory, CPU, and I/O. For CPU, we made use of CPU weight, which ensures that the transform process and the GVM would not use more threads than allocated. So far, would not interfere with other jobs executing or running on the same machine. Same thing with the memory. Memory has been the most precious or I guess most scarce resource for Spark jobs. So memory.max ensures that no transform job would go beyond the memory allocated to the container. And the jobs will be killed with, and also the resource manager will be signaled with feedback with an ohm kill. So the user would know that the transform process executed the memory allocation and was killed as a result. And also we ensured I/O latency, as you know, the machines share the same local disk. So we wanted to ensure that no transform process would saturate local disk and prevent other processes from running. So the combination of all these 3 controllers allowed us to ensure reliable transform operation. Now, also as an additional value of C group V2, that allowed us to be able to run multiple containers or multiple executors per machine, and having all these, each container could be belonging to different job. Since the isolation between these jobs is very robust, we are comfortable and able to run multiple containers that belong to different transform jobs on the same host. Given the isolation, will ensure that no job will step over other jobs' resources. Now, finally, we'll talk about future plans that we think we will do. 2 ideas comes in mind. So I mentioned Apache Arrow. Apache Arrow does try to solve a similar issue in terms of external process communication using a binary format. The main application today is in PySpark and Pandas UDF, which currently gives up to 100% improvement when it comes to vectorized execution. Apache Arrow is currently is used for in PySpark applications, but we in the future when the development is more mature, we think this could be also used for instead of unsafe row types. Also vectorization. Vectorizing currently we do as you saw in our examples. Spark would write 1 row, the transform process reads one row, applies the transformation, writes back the result row, and so on. A more efficient implementation will be to batch this operation. So serialize 10 rows, send them over to the process, apply the transform logic for all 10 at once, and then write back the results as a batch. Vectorization always improves the iteration, and I think the script transforms could benefit from it. So that's all to my talk, and I would like to take your questions.
Please raise your hand, and I'll bring the microphone to you.
Thank you for the talk. So in your examples, you give transforms that basically doesn't need any transform. I mean, it seems very simple.
Yeah.
So could you give some more complex example that you are using where you really need something like C++ or anything?
This example in particular, so that's actually a current use case, batch inference. So we have like an image model that classifies an image. So given any arbitrary image, this PyTorch model will predict the categories and give you the confidences. So today, PyTorch is actually the leading edge for image classification. Therefore, that use case we cannot foresee using or applying this ML use case inside of Spark itself, given the current environment isn't done in PyTorch. So it's a lot more effort. It takes a lot more effort and work to make it work with inside of Spark, inside the GVM, than using PyTorch runtime containers that exist today already.
But on the long term, would it be better to integrate those tools inside Spark instead of hacking Spark and trying to ship things?
Yeah, the question is, would Spark replace or do the same logic as TensorFlow or PyTorch? That could be possible, but as of today, I would say Spark is really efficient at ETL applications, but still for ML use cases, the frameworks of choice are not Spark still. The data scientists still use PyTorch and TensorFlow and other frameworks to apply their ML workload, especially when it comes to NLP or for some complex neural networks. That's always, from experience, have always been done on different platforms, PyTorch and TensorFlow or others, not inside of Spark. It could be possible in the future that Spark becomes the runtime environment for ML applications, but it's not the case yet. So therefore, we had to introduce the transform operator to make sure that we can use Spark and PyTorch together, in this case, efficiently.
More questions?
Thank you. So this looks really good, and I'd like to use it. So I heard you made some changes. So
yes.
Has it made it already to the main Spark? Or?
So there is already a Jira that's assigned to me for the transform operation. So yes, we'll merge these changes to open source. There's a Jira I can share with you that we plan to merge. It's not merged yet, but we're already on the way of doing it. Okay. So yeah, we plan to share these changes we made to Spark transforms in open source.
And is it already available somewhere?
Not yet, no.
Okay.
It will be. I will share the Jira number with you. I guess I'll open the screen so you guys can follow it.
Okay, thanks. And I had a second question. We had a job that was running some many iterations of very few short batches.
Okay.
And is there how are you dealing with starting the C++ process? Because if we want to do very short batches, the startup time may be quite long compared to the actual one. So are you dealing with that to not start too often the C++ process?
Yeah, so in this case, for that, I guess I will show you the slide in particular. So for short batches, ideally Spark would not be using a lot of small containers. So in this case, Spark will tune the input. So Spark would optimize its mapper stage. So instead of reading fewer rows and launching a lot of processes, we allow the user to control how big each transform process can process. So it's possible in Spark today you can override the input split size. So we can control that each transform process should take 1 megabyte or 10 megabytes or 100 megabytes of data. So if you could use a larger input split, which means fewer transform processes, at the same time, a longer latency. So that is up to the user to control the parallelism of the transform process.
We're out of time. Don't forget to rate this session in our app. And let's thank our speaker, Abdul, again.